Alright. So, let me begin with some notation. Atoms are usually measured in picometers or angstroms. So 1 picometer is equal to, how's y'all Swedish?
Swedish? No. No, I'm listening. Yeah, I don't know Swedish.
So 1 picometer is equal to 0.01 angstroms. Or equivalently, 100 picometers is equal to 1 angstrom. Named after a Swedish chemist, physicist, someone. So we've already done nanometer. Nano simply means times 10 to the negative 9 meters. A picometer is the spot directly under it. And by directly, I mean another down by 3. So negative 12 meters. So atomic radius is hard to define a precise way of measuring it. The proper way that we'll define the atomic radius is, let's look at nitrogen. Nitrogen exists as a molecule where it's 2 nitrogen atoms bonded together. Thus, if we have 2 nitrogen atoms, the radius is the distance between their nuclei divided by 2. So here's the radius, and here's the radius for 1 nitrogen and a nitrogen. So we cannot zoom down with a microscope and look at atoms. Not one that uses light, at least. We do have electron tunneling microscopes that basically send a bunch of electrons, and based on how much current or flow of electrons, we can turn that measurement into a distance and be able to generate a picture. It's not a picture that you would imagine. It's kind of basically like saying throwing baseballs at a wall and seeing that's not even a good analogy. It's like plotting the distance the ball traveled to figure out and reconstruct the picture. Another issue is the fact that, remember, the electrons are actually just a sea of probability, a cloud of probability. So if we have an atom by itself, we can't really talk about its radius because the electrons are just a cloud of probability. Not until we actually look at an electron does it form a particle and exist. Just like we can't really see probabilities, it's kind of hard to talk about the radius of an atom. Well, and also think about this. Which do you think would be bigger? A nitrogen atom by itself, or a nitrogen atom that's bonded to another nitrogen atom? Which would you think is bigger? Do you think they would be the same size? You would? Well, if you just divide it by half and just look at one of them attached to it. So the electrons here are going to all push on the electrons here. This nucleus is going to pull the electrons toward it. I would imagine that it would probably look more closer to something like this. It'd be oblong shaped, not a perfect circle. So when we talk about the radius of an atom, radius infers that we're talking about perfect circle. I'd expect two atoms attached to each other. The electrons will force this to grow taller, while the protons in the nucleus will pull and squeeze this down to where it's more narrow. So we can't really, another thing is, if we look at the noble gases, oftentimes you don't see measurements for the size of noble gases. Why is that? What's special about the noble gases? What's special about the noble gases? I've covered this before. So what do all atoms want to do? They're stable, so they all want to become stable. How do they become stable? They want to fill their valence electron shells. Noble gases have a complete complete shell, valence shell. So noble gases, the elements in the noble gas group, don't react with anything. They don't form molecules. They don't react. They're reactionless. You can force them to react in very extreme conditions, but normally you can. Anytime you look at a helium atom, for example, it's by itself. You will never see helium attached to another atom. Again, there's more complicated ways, well as the scope of high school level, to force helium to react. It's used in rocket fuel, for example. But normally it's by itself, and it's really hard to measure atoms by themselves. Another thing, this is physics, you don't need to know this. But basically, if you have a charge, so let's say we have a charge right here. It has a charge of Q1, so this is a charge to this. And you have another charge over here. Let's say its charge is Q2, and they're separated by a distance of R. Then this charge right here will exert a force on this particle. The force of the charge is equal to some constant times the charge of the first particle times the charge of the second particle divided by the radius squared. This is the equation that determines the force on the two particles. Newton's third law states that every force has an equal and opposite reaction. So whatever force this particle puts on this particle will put an equal but opposite force on the other one. So basically, if this particle pulls this particle with a force F, this particle will pull this one with a force F. They're equal but opposite in direction. Likewise, if this particle is positive and pushes this particle that's also positive away, this one will push equally back. The importance of why I'm giving this equation is to let you understand there are two major components that determines how strong the force is. One is the value of the charge. You increase the charge, force goes up. If you double the charge, you double the force. Makes sense? So, double the charge, double the force. You go from having a nucleus with two protons to 4 protons, and if you don't change distance, then the force is doubled. So if you keep everything else the same, the force is doubled. The charge of an electron doesn't change, but if you concentrate the charge in the center and double it, you double the force. The other thing is what happens if you change the radius. So let's say that the force. So the force is proportional to the inverse of the radius squared. So what this means, and gravity is the same way, what this means is if you double the radius, so let's say the radius is 2. Let's say that the radius is 2. Then the force would be proportional to 1 over 2 squared, or 1/4. If we double the radius, make it r equals 4, then it becomes 1 over 4 squared, or 1/16. So it reduces by a factor of 4. Whereas this increases by a factor of 2. So charge contributes twice as much. This is a square, or inverse square. So this changes by 1/4. Well, this changes by 2. So distance plays a significant role in determining force. And as distance changes faster, or causes force to change faster than the actual charge does. Does that make sense? So atomic size. The atomic radius is defined as the measurement of the distance from a nucleus to another nucleus divided by 2. So we usually only look at atomic radius after it's bonded to another atom. For oxygen and nitrogen, we're lucky that they form pairs of just 2 atoms. Think about this. I hate the fact that I have to keep switching. So, do you think... So, let's look at water. Water is an oxygen with a hydrogen and a hydrogen. And if we look at O2, which is an oxygen bonded with another oxygen, do you think that these 2 oxygens will be the same size or same shape? The forces applied to this oxygen is different than the forces applied to this oxygen. So we get into the weird thing to where the actual size numbers isn't really fixed and an exact value. We have to estimate it a little bit. Because if we compare the distance between the hydrogen atom nucleus and oxygen, we're going to get something different than if we compare 2 oxygens. That's why I'm going to have to pass out some notes when I finish making them. That'll show some tables and some values of all the atoms. But I'll put multiple tables so you can see. Some of the values change between them significantly. That's because there's different ways of measuring the distance or radius of an atom. And they don't always agree perfectly, yes.
When would you test corrections? When did the cutoff date for that?
Before the end of the 6 weeks. I prefer to have them done early, but progress reports, grades are going in Friday. If you want your progress report to be updated, you need to do it this week.
Okay. I'm supposed to be staying after school for tutorials today.
Alright.
Wednesday.
So, we've already went over this yesterday, going and deriving it. So, why is the atomic radius smaller as we go to the right? Why did the radius get smaller as we went to the right?
Because it had a false valence electrons.
As we go to the right, the valence electrons increases.
Oh,
We just went over this yesterday.
Because they have more electrons. They have
Electrons repel each other. It should make it bigger. The more electrons you add. Electrons will try to get as far away from each other as possible.
they would have more protons.
So more protons in the nucleus equates to a higher electrical force pulling the electrons closer. So remember, the electrons in a row, or a period, all have the same energy levels. So they're able to get pretty close to each other. But what we're mainly doing is increasing the charge of the nucleus by adding these protons. And this will pull all the electrons closer together to the nucleus. So, as we go down a group or a column, what happens to the radius? Does it get smaller or larger? It gets bigger, larger. Why is that?
Because they also have more protons.
More protons would pull them closer together. So, opposite charges would pull the electrons closer.
That's the one that has more electrons.
So it has more electrons.
It has more shells.
So one of the main reasons is due to the shielding effect. So the electrons can't get into lower energy levels because of Pauli exclusion. But what do the inner electrons do? They decrease the attraction between an outer electron and the nucleus of an atom. So the inner electrons will repel, pushing the outer electrons farther away. And also they kind of negate the charge of the protons. Also, being pushed farther away increases the distance from the nucleus, thus making the charge less, the force lesser too. So it's a double whammy right there. If they get pushed farther away, the force is going to go down because the radius or distance from the nucleus also decreases. But the electrons also shield some of that positive charge of the nucleus. So here's a nice picture. We can see that the outer electrons are being repelled by the inner electrons, and they're being attracted to the nucleus. This repulsion kind of pushes them farther out. So as we go down, the valence electrons are at higher energy levels and are not bound as tightly to the nucleus because they are screened or shielded, meaning pushed away by the electrons in the inner levels. So adding a new energy level as we go down the group means that when they attach to the atom, the inner ones are going to push them away. The going back to going across the row, we're not adding a new energy level. So remember the shape of the s orbital? The s orbital is just a sphere. And when we add an electron to it, basically it can go anywhere in the sphere. So its distance away doesn't matter. And also, going to the p blocks are these dumbbell shapes. So we can only have 2 electrons per dumbbell. So if we add one here, it's alright. We can make one the same distance away. So they're both the exact same distance away. Doesn't matter, they're on the same energy level. If we want to add some more, remember the dumbbell, there are 3 dumbbell shapes, or 3 p orbitals. We can also make them the same distance away. So that means they get basically the same strength, the radius doesn't change, and the electrons are going to pull the same. And there's also this one. So they can all be the same distance away. Whenever we add the next orbital is going to be most likely an S block. Well, they can't get into these dumbbell shapes because of Pauli exclusion. So they're going to have to be some spot that's farther away. These electrons are, now technically, the quantum mechanics, this can be right here. But these electrons are going to want to push this electron farther away so it never gets into the middle. Whereas when you don't increase the energy level, there's gaps it can reach into. There are some exceptions, which again, I'm not going to test you over the exceptions, but the major exception is column 13. So you should have your periodic table out always from now on. What is special about column 13? So let's look at the 4th period, one beginning with potassium. So potassium's electron configuration, and I'll use the noble gas configuration, begins with 4s1. As we go across the period, the next one is argon. Is calcium. So the 4th energy level picks up another electron. But let's look at the transition metals from scandium all the way up to zinc. Where do electrons go when we add them in here? They go to an inner energy level. The 3p energy level. And then when we get to group 13, which is the boron group, so gallium is the next one after here, its next electron is going to go in, so 4s2, 3p, oh, and I was wrong, these are supposed to be Ds. 3d10 and 4p1. So as soon as we get from zinc to gallium, we add another electron to the outer energy level. And so the transition metals, as I said much earlier in the class, are going to be the exceptions to a lot of rules. It's because of this jump between going to the outer energy level right there. So as we can see, as we go left to right, if you go to zinc versus gallium, you notice gallium's a little bit bigger. Also, if we go down the group 13, so if we look at boron and aluminum, as we go down, it gets bigger. But if we go from aluminum to gallium, gallium is a little bit smaller, I believe. This whole group doesn't seem to nicely line up with the rest. And indium is much bigger than all the surrounding elements. Again, I'm not going to ask you which is bigger, aluminum or indium. Are these exceptions, but just know that this group 13 is an exception. It's due to the transition metals. So, which is larger, a lithium atom or a fluorine atom? Hmm? Why?
It's got more protons.
So more protons makes it bigger? It's lithium. More protons pull the electrons closer to the center. Remember, as you go left to right, atoms tend to get smaller. That's because they're able to fill those p orbitals, and the nucleus is getting a stronger and stronger electrical force on the electrons.
Because it has more protons, it's going to pull the more electrons. That's why this is bigger.
Which is bigger, arsenic or sulfur? Arsenic. So as we go to the left, it's going to get bigger. As we go down, it's going to get bigger. So anything down left should be bigger than anything up right. It gained another energy level. And that was the major thing, is gaining another energy level. Ionization energy. Tell me what that means. What is an ion? What is an ion? Exactly.
Oh.
So how does it get a positive or negative charge? Hmm? Closer. How do you get a positive or negative charge? Electrons doing what? Come on. The last class was able to figure it out. So, ion is having an atom that gains or loses a charge. How do you gain or lose a charge? So again, your total charge is the sum of all your charges. So protons is going to be positive charges.
More protons and electrons be positive.
So how do you get more protons than electrons? How does an atom? So if an atom gains a proton, it's no longer the same atom. So how do you get more protons than electrons? You do what? Lose electrons. There you go. So what is ionization energy? The energy needed to remove an electron. It's in the name. So ionization energy is the amount of energy needed to remove an electron from a gaseous atom. The definition says gaseous atom because the electrons, when it forms molecules, is different. Because when an electron is being shared amongst the molecule, the energy can be different than when it's by itself. So we measure ionization energy whenever a single atom is by itself, and the only way to really get an atom by itself is to turn it into a gas. If it's a liquid, all the liquid molecules or atoms will be interacting with each other. If it's a solid, it'll be definitely interacting very strongly, keeping them bound together. What do you think the difference between first ionization energy and second ionization energy means? What do you think the difference? What do you think the meaning of the word first ionization energy and second ionization energy means? First ionization energy is the energy required to remove a single electron from a non-ion, from a neutral atom. The second ionization energy is the energy needed to remove an electron from an atom that's already lost one. So if we have, for example, let's look at beryllium. Beryllium has a +4 protons in the middle, an electron here, an electron like this. If we remove this electron, it takes energy to do that. This is the energy required to remove it, is the first ionization energy requirement. If you then remove this electron, so it's already lost one, but we're going to remove another one. This would be the second ionization energy. Note, the second ionization energy doesn't mean to remove 2 electrons at the same time. It means to remove an electron after one's already been removed. So remember that a positive ion is the removal of an electron, and a negative ion is the addition of an electron. Both take energy to do so. So what do you think? How do you think the energy, the ionization energy changes as we go down the group? So as we go from hydrogen to lithium to sodium to potassium, so down the group.
Going down to the left makes them bigger, right?
Yes, so it makes them bigger as we go down. So the atoms are getting bigger. So remember, as we go down a group, atoms get bigger, atoms' radius increases. So as we go down a group, what happens to ionization energy? The energy required to remove an electron from the atom.
If they're getting bigger, then that's adding electrons, right?
Mm-hmm. Well, no, because remember, as we go left to right, we're adding electrons and protons. So recall there are 3 things that affects the forces. There is the attractive force, between positive nucleus one negative electron. So if we increase the number of charges in a nucleus, pulls you, it's attractive. There is the repulsive force, between negative electrons and different energy levels. Technically, it's any energy level, but mostly it's from different energy levels. And there's also distance. So as we go down the group, we're adding a whole bunch of electrons, protons, and also picking up a new energy level. And the radius is increasing. So, which do you think is easier to do? Take a small atom and remove one of its electrons, or a big atom and remove one of its electrons? So, which is easier?
It's the take one from the smaller one.
This is where the radius plays a greater role. As you move down a group, the energy requirement decreases. This is because the size of the atom gets bigger and the electron is further from the nucleus. Remember that in the equation it's r squared. So if you get farther away from the nucleus, that pulling power isn't as strong. And so as you get farther away from the nucleus, since r is squared on the denominator, it's going to significantly reduce the force holding it to the atom, and it's easier to remove. So, what about going left to right? Would ionization energy increase or decrease? Why would it decrease?
Because they're having more protons, more, the protons are pulling the electrons in more.
So that would decrease the energy requirement to pull it?
You said it would increase.
Oh, did you say increase or decrease?
Increase with the protons.
Yeah, so it would increase. So basically we have a situation like this. We have a nucleus, and we have this dumbbell shape. But add an electron, let's say here. And let's say that we go to the right, and we're going to have a nucleus, this dumbbell shape. But we're going to add another proton. So this gets stronger, which is going to pull the two electrons closer together to the nucleus. Because this is increasing by a +1 charge, is stronger than the nucleus on the left. But we're not changing energy level, so this electron is free to choose an energy level such that it's on the opposite side. If it makes it even easier, think about planets orbiting. So that's actually a very good analogy right there. If we have the Earth and the Moon, what would happen if we make Earth bigger and then put another moon on the other side of the same size? The gravitational effect is going to be stronger on both moons. But the gravitational effect of each other isn't going to really matter too much because the moon is so much smaller than the Earth. Gravity doesn't work too well because there's no anti-gravity. technically this would always bring them closer together because of gravity here. But if you ignore the repulsion of the electrons on each other when they're in the same energy level, it makes more sense. So as we go down, as we go left to right, the energy level increases. This is because the nuclear charge increases, while the shielding, meaning the inner electrons, doesn't change. The inner electrons don't change as we go across a period. We're not increasing. We're only adding electrons to the valence shell. This means the attraction of the electron to the nucleus is going to increase because it has more charge. And we can ignore the repulsion in the same energy level. This is a super blurry image, but it's really good at the same time. So we can see here the height of each square represents the total energy required to remove an electron. So up to the right requires the most energy. It's really hard to remove the electrons from fluorine. The energy to the left and down doesn't require that much energy. So as you go left to right, the energy significantly increases. As you go down, the energy also the energy decreases, but not by as much. And you can also see here's another exception related to the transition metals versus the ones to the right. It's my recording software. I was trying to move this window back over here, but I moved my recording software that's recording that screen over there. So it creates infinite images of itself. This will not be needed, but I'm going to use it to explain something. We will have an entire unit on each of these. Maybe not the one I'm covering right now. So you don't really need to know this. There are 3 major types of bonding. Ionic bonding, we'll have a unit on that. Covalent bonding. And metallic bonding. I'm bringing this up because if we look at metallics, or metals, do you know how metals actually bond to each other? So let's look at copper. Or iron. I'll use iron, I used that last time. So we have iron atoms all together, and they all have electrons going around them. However, the energy to knock off this electron isn't that much. So occasionally, this electron will move over here. This atom becomes negatively charged. This atom becomes negatively charged. This atom becomes positive. It lost an electron, and this one gained an electron, so it's negative. This means that there is a charge difference between these 2 atoms, so they're pulled together. This electron then hops back, and they're neutral. And occasionally, this electron will move over here, and there's a slight pull around here. In metals, it's called a sea of electrons. All the electrons are constantly moving around all the atoms. And what ends up happening is some of the time they're negatively charged and positively charged, and that pulls them together. If we get 2 atoms that are negatively charged and will repel, this usually doesn't happen much because immediately an electron will come over here and make this neutral. which then would make this positively charged, and then these two would attract. This is the reason why metals conduct electricity. So let's say we gave some force on the electrons. Let's say we push them. Well, this electron here will be pushed toward the right, which makes this one positively charged, and means it's going to pull an electron over to the right here. And if we continue to do this, what we see happening is a cascade of electrons jumping from one atom to another. If we apply a voltage that forces the electrons to go in a certain direction, then this is actually how electricity works. When we say there's a flow of electrons moving in a wire, it actually is not the same electron moving. It's one electron hopping to another atom, and randomly one of its electrons will hop to the next, and they're hop, 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 and continue on like that. I'm bringing up metals because there's the idea of metallic. So here's also the ionization energies plotted. We can see each color represents a row. So as we go left to right on a row, the energy requirements increase, but as we drop down to the next period, it significantly fall off. So metallic elements easily lose their electrons. Non-metallic metals more readily gain electrons. So this is what makes some elements metals, and some elements non-metals. Bell's about to ring, right?
Yeah, less than a minute.
I just want to show you all this one picture really quick. We can see where all the metals are. And we can see where all the non-metals are. In between, there's something called metalloids that have enough energy to be considered, has some properties of non-metals, but also don't have enough energy so they act like metals. So they're right in between. But this is actually what makes all the metals, is ionization energy. All the non-metals have high ionization energies, and thus their electrons can't keep them together without forming chemical bonds. But we'll continue tomorrow.